Hi students, today let us discuss about the colorimetry. There are two important questions under this colorimetry. Number one is derive combined Beer-Lambert's law and mention its any two applications. Number two, explain instrumentation of colorimetry and mention its advantages and limitations. These are the two questions. Let us take number one, derive combined Beer-Lambert's law, which is the basis for colorimetry, and mention its any two applications. So under this derivation, first let us take Lambert's law. Lambert's law, the name implies Lambert's law is related to its length or length of the medium or thickness of the medium or length of the test tube. So according to Lambert's law, when monochromatic light means which is having the same wavelength, that is monochromatic light. So when monochromatic light passes through a transparent medium, the rate of decrease in intensity with thickness of the medium is proportional to the intensity of light. Mathematically, it is expressed as minus di by dl. Minus indicates decrease in intensity. So change in intensity. Di means change in intensity. dl means change in thickness or length, and is proportional to the intensity of light. So minus di by dl is proportional to I. When you take one constant, that is k, minus di by dl is equal to ki, equation number 1. So on rearranging this equation 1, we get finally minus di by I is taken here and dl is taken here. So minus di by I is equal to kdl, equation number 2. Then by integrating the equation number 2 between the limits, I is equal to I0. I0 is the lower limit and IT is the upper limit, and L is equal to 0, lower limit, and L is the upper limit. So here, when you take integration on both sides, then integral minus di by I is equal to integral kdl. According to the formula integral 1 by dx, this becomes ln. ln I0 by IT is equal to k into L. So k is constant. So integral dl is equal to L. That is why k into L. Then equation number 3. Actually, after substituting the upper and lower limits, we got this ln of I0 by 8 is equal to k into L, equation number 3. Next here, we know that ln is equal to 2.303 into log. ln is natural logarithm and log is common logarithm. So by changing into common logarithm, we get the equation here 2.303 into log of I0 by 80 is equal to KL. Instead of ln, we have taken here 2.303 into log. Next here again, log of I0 by 80 is equal to K divided by this 2.303, it will be divisible. So K by 2.303 into L, where K by 2.303 is equal to capital letter K, and it is termed as absorption coefficient. Then again, this can be written as log of I0 by IT is equal to capital letter KL, equation number 4. Then after equation number 4, the ratio of IT by I0 is termed as the transmittance T. Its reciprocal I0 by IT is the opacity or absorbance. Therefore, the absorbance of A of the medium is given by A is equal to log of I0 by IT. Then thus Lambert's law can be expressed as A is equal to log of I0 by IT, which is equal to capital letter KL, equation number 5. Then when you take Beer's law, Beer is one of the name of scientist. According to him, when monochromatic light passes through a transparent medium or solution, the rate of decrease in intensity with concentration of the medium. So Lambert's law is the uh, based on the length of the medium. Here, Beer's law is based on concentration of the solution. That is why here, when monochromatic light passes through a solution or transparent medium, the rate of decrease in intensity with concentration of the medium or absorbing medium is proportional to the intensity of light. So mathematically it is expressed as same way, minus di by dc. Dc is the change in concentration is equal to k dash I. So equation number 6. On rearranging this equation 6, we get minus di by I is equal to k dash dc. This is equation number 7. Then integrating the equation number 7 between the limits I is equal to I0, I is equal to IT, and C is equal to 0, and C is equal to C. So integral minus di by I is equal to integral k dash dc. So according to the integral formulas, this becomes ln of I0 by IT is equal to k dash C after applying the upper limit and lower limits. This is equation number 8. Then, so by changing into common logarithms, equation number 8 becomes 2.303 into log of I0 by IT is equal to k dash C. Log of I0 by IT is equal to k dash divided by 2.303 into C we can write. So that is why where small k dash divided by 2.303 is equal to capital letter k dash we can take, and it is termed as absorption coefficient. Therefore, A is equal to, A is nothing but absorbance, is equal to log of I0 by IT is equal to k dash C, capital letter k dash C, equation number 9. So from equation number 5 and 9, okay, we get a combined equation, that is here A is equal to log of I0 by IT is equal to epsilon CL. Instead of taking k and k dash constants, we can take one more constant, that is epsilon. Okay, so here from both the equations, we can directly write it as A is equal to epsilon CL, where epsilon is the molar absorption coefficient, C is the concentration of the solution, and L is the length of the medium or test tube. So this is equation number 10. Equation number 10 is the combined Beer-Lambert's law, and it is the fundamental equation of colorimetry and spectrophotometry. So based on this, there are two applications explained here, that is number 1 in quantitative analysis, which we are going to do practically in chemistry lab. So here, how to explain this quantitative analysis? A large number of metal ions which forms color in the complex. Number of metal ions, anions, and organic compounds can be determined by colorimetric method. For example, copper content in a solution can be colorimetrically determined using aqueous ammonia as the color developing reagent. So here, when you take copper sulfate solution or copper chloride solution, copper chloride solution contains copper 2 plus ions. These copper 2 plus ions react with ammonia to form a deep blue colored cuprammonium complex ion, like by the following equation. So Cu2 plus ammonia, and it forms CuNH taken 4 times and whole power 2 plus. So this is the deep blue colored cuprammonium complex solution. Then here, okay, here in this experiment, a series of copper 2 plus ions, standard solutions, a series of standard copper 2 plus ion solutions are prepared, and color in each of the solution is developed by the addition of a definite volume of the aqueous ammonia to develop the color. Then the absorbance value of the standard solutions are measured against a reagent blank, okay, using a colorimeter at a wavelength range corresponding to a maximum absorbance. So in this experiment, we are going to, okay, select the filter, that is 620 nanometer filter, because at 620 nanometer filter, our complex or our solution observes a maximum radiation. That is why in this experiment, we are going to choose 620 nanometer filter. Then a calibration curve as shown below is obtained by plotting absorbance against concentration. The test solution in which the concentration of copper 2 plus ions is to be determined, okay, is also treated with ammonia to develop color. Actually here, by the addition of ammonia with a test solution, the test solution means whose concentration or amount of copper 2 plus ions to be determined, that is test solution. And by adding ammonia, color has been developed and its observance value is measured using a suitable blank solution. Blank solution is nothing but without containing metal ions. Without containing metal ions. Only ammonia and distilled water is taken and it is made up to the mark. That is called as blank solution. Then and its absorbance is measured as the observances are measured with standard solutions. Then from the calibration curve, the concentration of the copper 2 plus ions in the solution can be determined. The graph is shown here in this experiment here. Concentration of the solutions are taken on x-axis, then observance values or optical density values are taken on y-axis. When you take 1 ml standard solution, it gives somewhere observance, okay, here. Then when you take 2 ml concentration, copper 2 plus ion standard solution, it gives observance. 3 ml, it gives observance. Then when you plot a curve, when you plot a curve, so the line passes through the origin is called as calibration line. From this calibration line, okay, we can determine the amount of copper 2 plus ions present in a test solution. The test solution observance is measured on y-axis somewhere, and the observance of test solution, okay, uh, from that observance of test solution, directly a straight line is taken to calibration line. From calibration line to x-axis, it gives somewhere. Then by knowing the concentration and the amount of copper 2 plus ions is measured. So this is the first experiment which we are going to do in engineering chemistry lab. Next, second application of colorimetry is photometric titrations. So colorimetric measurements have also been used in locating the equivalence point or end point in a titration, where one of the species, either the titrant or reactant or the product, has a specific observance. That means here one of the species should observe the observance. Then only it is possible to measure the observance of any species, and in turn the uh, amount of metal ion is measured. Then in such a case, the plot of observance versus volume of titrant added consists of two straight lines as shown in these two graphs, okay, intersecting at the equivalence point. This is the equivalence point here. Then at the equivalence point, okay, if the reaction is complete and the volume change is very small. If the reaction is if the reaction is complete, volume change is very small. So here some typical plots are given below here. So A and B. So what kind of information gives A kind of graph, and what kind of information gives by B graph? So here, look at here, A graph, reactant observe the observance, whereas titrant does not observe the observance. That is why graph is like this. This is the equivalence point. And when you take B type graph, titrant observe the concentration or observance. Titrant observe the observance. Titrant observe the observance, and reactant does not observe any observance. That is why, okay, graph is like this. Then the straight lines. When you extrapolate these two straight lines, intersect at this point. This is called end point or equivalence point of the titration. So these are the two applications of colorimetry. Okay, next is advantages of colorimetry. What are the advantages? Colorimetry, number one, colorimetry gives more accurate results at low concentration than corresponding titrimetric or gravimetric procedures. Okay, number two, method may frequently be applied under conditions where no satisfactory results of gravimetry or titrimetric procedure exist. The method is simple and rapid possess advantages for the routine analysis. And limitations. Number one, similar colors from interfering substances can produce error in results. So when any same species produce same color, then it is difficult to apply this method. So it may give error. Number two, more precise analysis can require tighter wavelength bandwidth. Tighter wavelength bandwidth. So here to get accurate analysis, so tighter wavelength bandwidth is required. Actually, so higher version filters or higher version monochromators are required. So those higher version monochromators are little slightly expensive. Next, third one, matrix inferences. Matrix means the number of metal ions in a solution. Complex. So here, matrix inferences can produce bad results in uncontrolled situations. So these are the limitations. So next, instrumentation. Under this instrumentation, so we have to draw this diagram. So under this diagram here, light source. Light source is nothing but normal light. So from normal light, we can get radiation through the slit, and the radiation passes on lens, and the radiation, okay, which comes from lens, pass on filter. This filter, okay, filters the required wavelength of radiation. So that radiation, okay, passes on the solution, so which is called as cuvette, small test tube, so called as cuvette, and some of the radiation is absorbed by this solution, and remaining is reflected. The observed radiation is converted into electrical signal by using photoelectric cell as output, that is absorbance. So these are the important parts of digital photo colorimeter. So here, to explanation about this instrumentation, colorimetry is one of the spectroanalytical methods. The variation of color of a solution with change in concentration of some solute component in the solution forms the basis of colorimetry. Colorimetry is concerned with the determination of the concentration of a substance by measurement of the relative absorption of light with respect to a known concentration of the substance. Actually, earlier we were using visual colorimetry. In visual colorimetry, uh, uh, human eye is okay were present. Human eye was present. So here, but here when you take a photoelectric colorimeter, in photoelectric colorimeter, photoelectric cell is used. So that is digital photoelectric or digital photocalorimeter. So visual colorimetry or visual colorimeter is colorimeter consists of human eye. But when you take digital photocalorimeter, consists of photoelectric cell. So this is the difference between earlier visual colorimeter and digital photocalorimeter. So this is about instrumentation of digital photocalorimeter. So thank you.